Hey, Jan, thank you for coming in. I mean, you're legendary. You just got the Queen Elizabeth Engineering Prize with your colleagues. And of course, earlier you had the ACM Turing Award, which is the Nobel Prize of Computing Science, and so many other recognitions and honors for all of the transformational work you do and you continue to work. And of course, you're heading up all the great work at Meta as well as chief scientist at Meta. So again, thank you for coming in and sharing your insights with my audience.
It's a real pleasure to be here. Thanks for having me on.
So, Jan, you got this remarkable career, and what were the inflection points in your life that created this remarkable career and continues? Now, it could have been when you were 3 or 5 years old, inside, outside the family, inside, outside of school. It could have been mentors that you've had. So, what were those three sort of magic moments, inflection points that created who you are today?
Yeah, I might have to go quite far back. So my dad was a engineer, mechanical engineer. He was working in the aerospace industry and was always very creative himself. He taught himself electronics and he had a hobby of building model airplanes. He got me into this when I was a kid. Maybe I was 7 years old or something like this. He got my younger brother into it as well. My younger brother, who is actually a working at Google Research.
That's
So, but not doing machine learning. It's doing optimization, operations research. But anyway, so I learned, how to kind of design and build things from my dad essentially, and was really interested in early on in, a lot of questions. I grew up in the '60s, so this was, when uh, the world, the entire world was talking about rockets and computers and things like that. And the idea of AI was really science fiction at the time. Um, but when I was 9 years old, I my parents took me to watch 2001: A Space Odyssey, and this had like all the themes that are fascinating, right? It's like space travel, what's the universe made of, how human intelligence emerged. So, 2001 has kind of a theory about this, that it was kind of seeded by aliens or whatever. And then also intelligent computers, right? And so all the themes that I thought was fascinating when I was, a kid, were kind of condensed in that amazing movie. Still my favorite movie of all times, to this day. And I thought the idea of kind of understanding human intelligence by building an intelligent machine was really sort of a fascinating topic that I was always interested in since I was a kid. So I studied electrical engineering after high school and got more and more interested in AI and things like that. So I did a few independent projects during my engineering studies on things like that, and discovered that nobody was working on machine learning at the time. There was not even a thing. Like there was no domain called machine learning at all. But people in the 50s and 60s had worked on uh, what we now call neural nets or deep learning, with limited success, and the whole field disappeared in the late 60s. So I was kind of plowing through the old literature when I was an undergraduate student. We're talking 1980 or so, um, and discovered that people had been interested in this, had stopped being interested in this. So when I graduated in 1983, I tried to figure out if I could do a graduate school and work on this topic. And the problem I had is that nobody was working on this in France. And so I had a hard time, finding people who might, sign the papers for advising me to do a PhD. And I found one. I had who actually started working on neural net after I graduated. I got him into it basically, and and then met Jeff and Terry Sanofsky and a bunch of people while I was doing my PhD, and that's how I started.
So kind of a remarkable journey. I mean, your dad was an engineer, so he got you interested in tinkering and things like that. So very translational, right? Because engineering is very practical. So you're looking at sort of the practical applications of this, and then you go into this 2001, it's an amazing movie because it introduces this idea of hell, and there's a philosophical side of it, and computing and the possibilities. Now we're entering into that kind of era where
Yeah.
all is capable. You're continuing your studies in engineering and more, and you were able to get somebody to be your supervisor in your PhD work because
Well, there was an independent lab in Paris that was put together by people who had faculty positions in various places in the universities around Paris, and they were all interested in a question of what happens when you connect lots of simple elements with each other. Like what kind of dynamics can you observe, right? So those people were interested in, the general problem of self-organization and things like this, but not really connected with neural nets at the time. And so that within that lab, there was, one gentleman, Maurice Milgram, who was a full professor, so you could advise PhD students. You can advise PhD students in France if you're not a full professor, basically. And he told me, I asked him if he could be my advisor, and he said, well, I've no idea what you're working on, so I can't help you from the technical point of view, but I'll sign the papers. You seem smart enough. So I had independent funding from my engineering school, some sort of scholarship. So I didn't need any funding, so it was easy. And my engineering school, where I had done my undergrad, also had fairly powerful computers for the time that I could use. So that was something that not many people had access to at the time.
Yeah, and then you do your postdoctoral work with Jeff Itten, right, at the University of Toronto. So
yeah,
describe that.
Right. I met Jeff in 1985. So I graduated in 1987 for my PhD, but in 1985, early 1985, I'd met Terry Sinofsky. So he's the co-author of the Boston Machine paper. And I really wanted to meet him or Jeff because they were the only people who understood that to kind of lift the limitations of the early models from the 60s, the perceptron and things like that. You had to basically train neural nets with multiple layers. And Boston Machine was basically one of the first algorithms that could do this. So when I read this paper, I really wanted to meet them because they really understood what the problem was. So I attended a workshop in early 1985 where Terry gave a talk, and I gave a talk. That was my first talk in English. I was terrified, but Terry arrived later at that workshop, so he didn't hear my talk. So I cornered him one afternoon and explained to him what I was working on. He went back to the US and he said, there's a kid in France. He said to Jeff, there was a kid in France who was working on the same stuff we're doing. And at the time, Jeff was already working on backprop, and Terry also was working on what was called NetTalk. It's a backprop network that could learn to pronounce English, basically. So then a few months later, Jeff comes to Paris for an invited talk at a conference where I had a paper, and he gives an invited talk on Boston machines. And then after that, a lot of people wanted to talk to him, and I couldn't approach him. And he turns to the organizer and says, like, do you know this guy, Jan LeCun? And I say, oh, I'm here. And he had read my paper, in French in the proceedings and figured out it was, something kind of like backprop. I was kind of describing an algorithm that we would now call target prop, but it was like very similar to backprop. And so this was before backprop was published, right? So by him and Dave Eberhard. So so we had lunch together, and basically we could finish each other's sentences. Like we knew exactly what what the problem was, how to approach it, and like we had a common view and everything. So that's how he offered me to do a postdoc with him after I graduate, and he was on my thesis committee. So.
Yeah, I mean, it's really quite remarkable. And then you had this CFAR, this kind of Canadian sort of advanced research establishment, and then prior to NeurIPS, there was this conference that they were supporting, and you three, I guess yourself, Jeff, Joshua, and others would meet in the back room, kind of discussing where where things are going, right? Can you describe the CFAR work in the early days of NeurIPS,
Okay.
where it was called NeurIPS?
Well, that came much later. So the event I was describing was, 1985, 87, right? I did my postdoc with Jeff in 87, 88. Um, and and then I joined Bell Labs. I was recruited by Bell Labs because I met them also at the same meeting in early 85 where I met Terry Sinofsky, and they eventually offered me a job. So I stayed at AT&T for a dozen years or so, then worked briefly at the NEC Research Institute in Princeton, and then joined NYU in 2003. And that's when Jeff Hirscher and I kind of got together again. So Jeff had been in the UK for a few years and then was coming back to Toronto, and I was approached by CFAR to start a program in basically on neural nets that he called NCAPS. That meant neural computation and adaptive perception. And he had a couple preparatory meetings where we discussed what this should be about. At first, this program could only fund Canadian scientists. So being in the US, I was on the advisory board, essentially. And we used this. So the program started around 2004, 2005, something like that, and 2005. And basically, we used it to kind of get together, the three of us, but with people interested in kind of similar questions, with our students. We organized summer schools and various things to basically create a community around neural nets and what we later called deep learning a few years later. And it was necessary because the entire machine learning community was dead set against the whole idea of deep learning and neural net at the time. It was kind of the subject of mockery, actually, more or less. So we had to have create kind of a safe space, if you want, to sort of develop a common language and methods before the community was large enough that when we submitted a paper to a conference, it would be reviewed by other people from the same community, right? So that started happening around 2007 or so, and 2008. And then the first really practical success of deep learning happened around 2010 in speech recognition. And then, of course, in 2012, there was kind of the ImageNet, kind of revolution, which made all the big companies starting to pay attention to deep learning, and also the press. And of course, we couldn't explain to the press that deep learning was not what people commonly call AI, and so they called it AI, and now we had to call it AI, and that became a branch of AI basically. But then it took off, and that's when Google started getting into this in 2011 or so, and Microsoft a little bit also, 2011, 2012, IBM around the same time for speech recognition, and then Facebook, in 2013. That's when I joined at the end of 2013. And then, a Chinese company like Baidu and, a few others. And so it took off around that time. So the conspiracy that Jeff Hirscher and I started in 2005 or so to, renew the interest of the community in deep learning sort of succeeded beyond our wildest dreams, essentially.
Yeah, you would have trouble getting acceptance from the broader community early, right? Like getting your papers accepted and things like. What was that? What did that feel like?
Yeah, between the mid 90s to the late 2000s, it was basically impossible to get a paper, into a major computer science conference about neural nets or deep learning. There was kind of a separate community that was specifically about neural nets, but they didn't have much of an impact outside of their community, and they were kind of looked down upon by computer scientists, So it was a bit painful. I in the early 2000s, late 90s, I connected with the computer vision community because I thought the biggest likely impact of deep learning was going to be in computer vision. I had worked on pattern recognition, visual pattern recognition, handwriting recognition, things like this before face detection. And I thought it was time to kind of try to solve real, natural images, like recognizing objects in natural images, things like that with neural nets. And that's what my lab at NYU was mostly doing in the mid 2000 to late 2000, with some success, but the data sets at the time were so small that it didn't actually favor learning-based approaches. It favored approaches where most of the system is basically hardwired because the data sets were so small. And so we're getting decent performance, but not record-breaking. And it's only when ImageNet became available. So there was, 1 million training samples and 1,000 categories. And the secret there was to implement large neural nets on GPUs, which my lab at NYU was a little late doing because we were busy with some other project that we were embroiled in, some DARPA project. So that fell upon Jeff, basically, with his students, Elias Iskaver and Alex Krzyzewski, to have the most, smashing demonstration that those things were really working well.
Yeah, I mean, the Queen Elizabeth Prize, which is a really prestigious prize, was announced just not that long ago. And of course, Fei-Fei Li got some recognition because of ImageNet, right? With you and Joshua and Jeff and others. So Hopfield and other, it's great to see how you get this kind of recognition, including Fei-Fei Li, right?
Yeah. So the prize was they kind of split it into three, right? There is one part was basically foundations and methods. So this was for Jeff, Joshua, and me. The second part was for hardware, and that was Jensen Huang, the CEO of NVIDIA, and Bill Daly, who is their chief scientist. And then the last part for data, and that's for Fei-Fei. So I mean, she collected the data and had it labeled, and it certainly had a big impact.
But you were already doing translational work, which was useful in things like checks and so on way before, right? In your convolutional neural networks, right? So.
Yeah, I mean, convolutional nets were already used industrially. So in the mid 90s and late 90s for things like check reading and various sort of document reading, digitization. For checks, it was pretty large scale. So my colleagues at AT&T built a practical software system that was deployed in check reading machines sold by NCR, which at the time was a subsidiary of AT&T. And at some point in the late 90s was reading on the order of 10 to 20% of all the checks in the US. So it's, a major application, right? Big deployment of convolutional nets of the type that we knew in the early 90s. And then after I joined the NEC Research Institute in Princeton in 2002, NEC kind of started to get interested in this thing. So we developed a system to do real-time phase detection and pose estimation, which worked really well. And then some of my colleagues at NEC got interested in using convolutional nets for other things like estimating the age of a person and the gender and things like that. And the reason they got interested in this is that they had two interests. One was video surveillance, basically, but the other one was, and so they were also working on face recognition and face detection and person detection and things like this and using convolutional nets. And the other thing they were interested in is they deployed actually an application which was a vending machine deployed in Japan in, train stations and places like this. And that vending machine would look at you and determine your gender and age, and then address you in the appropriate way, because that's going to be important in Japan, right? But also propose different products depending on you. They deployed this also on like advertising panels and things like this that basically changed the topic depending on who is in front of it. So they had a bunch. I mean, by that time I had left NEC already. I only stayed 18 months, and I joined NYU. But there were a few of those applications for like, biological image analysis and phase detection and various other things that people had deployed over the years in various contexts. What's interesting, though, is that in 1990, when we developed the first convolutional nets at AT&T filed a patent on them, actually two patents. And And technically, those patents would stop anyone from, using convolutional nets and deploying them commercially. But in fact, the patents were, AT&T broke itself up in various places in various ways. And the patent ownership ended up with the NCR Corporation, which had no idea what they had. So, and thankfully, those patents expired in 2007. So it was very difficult. It would have been very difficult for salespeople to do like major deployment of convolutional net before 2007 without getting into legal trouble.
Yeah, it's kind of fortuitous for the world, though, and you're foundational to all of this. So I can see this going back to your engineering roots with your dad, right? It's very, very practical application, and your family must be really happy with where this has gone, right?
Well, surprised it arrived, fairly late, but yeah, it's kind of a interesting turn of events.
Yeah, I'm just thinking, Jensen Huang didn't realize the value of GPUs really back before 2010 or 2012, I guess.
Or later than that. Yeah, it was at least 2012 or 13. I mean, there were like a few people who were trying to use GPUs for neural nets there. They weren't using the kind of neural nets you use now, so I don't think he paid much attention to it. I think it started to become really big in 2013, essentially.
Yeah, and then now it's 3+ trillion. I mean, it changes, like DeepSeek kind of caused a little bit of a reset, but it's go back up again, right? And it's interesting what DeepSeek did is kind of democratized. And of course, you've been a big proponent of open source, but we'll get to that a little bit later. So did you meet with Jensen before 2013 or 12, or have you got to talk to him at all?
I talked to him, so I can't remember if it was early 2013 or late 2013. I think it was before I joined Facebook, so it must have been early 2013. And talked to him and his team, and we talked periodically after that. But it was already pretty clear that GPUs were going to be an important component of kind of the future of AI. I mean, not necessarily as big as it become, because I mean, what happened then was interesting. I was also talking, before 2000, like around 2012 or so. I was talking to various companies who are actually working on neural net hardware because they were kind of seeing this thing taking off. So that included Intel. They actually started a project in Israel to build neural net accelerators, essentially, in sort of multi-core CPUs. Another company called Movidius, which eventually was acquired by Intel, actually. And they were kind of more targeting embedded devices, so kind of the low end. There were a company that were like traditionally making DSPs, and they say, well, maybe neural nets are kind of a good way to sort of transition to other type of applications. They were eventually bought by Intel. Intel kind of didn't do much with it, and the CEO of the company is now CTO of STMicro, which is the big European semiconductor company. And I talked to Mobileye. So Mobileye went through an interesting transition around 2012 or so, or 13, where they're a company that built vision systems for cars, for driving assistance for cars, based in Israel. And they were not using convolutional nets. They were using, some more traditional vision technique. But they had a chip, special purpose chip, to run their algorithm. And a professor from Israel kind of sat in one talk that I gave in 2012 or 2013. And basically was interested in convolutional nets and was just about to do a sabbatical at Mobileye.
Yeah.
So he started a sabbatical in summer 2013 or something, and tried to convince them that you should use convolutional net, and said, no, we don't think that's a good thing. So he kind of implemented them and showed they work really well. And they were kind of amazed, and they decided to basically switch to using convolutional net. But the problem is that they already had a chip that was designed for something else. Now, thankfully, that chip had a convolver in it. So now what they had to do was shoehorn the convnet that they had trained onto their chip and then redesign another chip, obviously, for next generation. But eventually what happened is that their system, based on convolutional net, they sold that system to, or the license at least, to Tesla. And so the first, driving assistance system in the Tesla that came out in 2015 used convolutional nets from Mobileye. And then in 2016, Mobileye decided that Tesla was not using their system properly. And so they thought it was unsafe, actually, the way they were using it. So they stopped the partnership with Tesla. And Tesla had to basically implement their own thing and start a group that worked on self-driving from scratch. They couldn't reuse the vision system from Mobileye. And it took them 2 years to basically kind of, match the performance they had with the Mobileye system. But eventually they did.
You're so foundational to all of this. But you see these valuations, like Fifi Lee has started her own company. You've got the, a past OpenAI people like Ilya, who's raising around a 20 billion valuation, I think, is Safe Super Intelligence. You had Jeff and Alex and Ilya do an early exit to Google for 45 million, I think, or something like that.
Something like that.
Yeah, but then you see these billion valuations. Now, Jan, have you been able to monetize some of this amazing innovation you've done? Can you describe maybe some of your translational commercial work in some way, or
Okay, well, probably not, to the extent that you might expect, quoting those numbers, because at the root of it, I'm a scientist. I'm not a business person. I'm not a CEO. I've co-founded a bunch of companies, but not really sort of that being my main activity. So, I'm a distant entrepreneur, if you want, but not not completely involved. I'm really a scientist. That's what I want to spend my time doing. Now, I share my time between being a professor at NYU and being chief AI scientist at Meta. For the first 4 years I was at Meta, I created the what we call FAIR, which at the time meant Facebook AI Research, and now means Fundamental AI Research because the company changed it. So it's called Meta FAIR. I ran it for 4 years. But again, that's not what I wanted to do with my life. I'm really a scientist. So I went back to research. So as a chief AI scientist, I'm not actually running any organization. I'm basically inspiring people to work on things that I think are interesting. I come up with my own ideas. I try to associate with younger people who can actually make them work and things like that. But both at NYU and at Meta. But the FAIR is run by Joël Pinot. So the lab had a huge impact on Meta, and I'm not running a 20 billion company or anything, but that's not what I want to do in my life. I'm doing fine financially. Like I don't need money. It's fine. I'm not like super rich, but I'm I'm pretty well off, so I don't have to worry about this. And I do what I enjoy doing, which is really pushing the science and the technology and having an impact on the world and hopefully making it a better world.
Yeah, and I remember because I've been on the board or board committees for a long time, since like 2009 with ACM, right? And then internally we get this announcement that you're going to get this thing, and then of course you get the ACM Turing Award, which is a pretty big deal, right? It's like the Nobel Prize in Computing Science in 2018. What was that like? Because that's really recognition at the ultimate level, right?
Well, it's as big as it gets for computer geeks, right? So yeah, I mean that was incredible level of recognition. I mean it's not something you plan for, obviously, right? You just do good work, and then um, I mean the work that I'm most recognized for is work that I did when I was in my 20s and 30s, early 30s, right? So it's going back a long time, late 80s, early 90s, and there's a lot more things that I've done more recently, which I think are also really interesting, but they're not going to get this level of recognition for a while. Um, that's the that's the issue with basic research. Like the actual impact of what you do may be a long time in the future. You have to accept that, essentially, unless you want to go into development and product development and things like this. But again, I see myself really as a scientist and an engineer, or a scientist in a domain that is engineering science, where you create new artifacts, and then you use the methods of science to actually kind of make it work and analyze it and make it better and things like that, right? But there is an engineering field. You create new artifacts. Very creative activity, which I like, which is the part of it that I really like. So, yeah, I mean, it was a bit of a shock because the ACM, the chair of the committee was Alfred Spector at the time. The ACM Turing Award Committee could not reach me. I was in France, and the phone number he had was my professional phone number, which is always on silent. So I didn't pick up the phone, and he had trouble reaching me, and eventually reached me. It was late in France. I was about to have dinner at my brother's house, and I said, like, is that a joke? It wasn't a joke. So that was a bit of a shock. I was really happy that both Jeff and Joshua and I got it together. That was great.
Yeah, and you've been colleagues for so long, and you used to meet sort of at the side with the NeurIPS and the predecessor NeurIPS as well, right? So, and you've been with CIFAR so for a long, long time. So it's kind of a culmination, and it's from a computing science standpoint, it's the ultimate recognition, right, of your peers that you've done stellar work that long lasting. It's based on long lasting work, right? It's not based on momentary things, but things that have a profound impact in your field of computing science generally, but profound impact.
That's true. And there were, in the early days, particularly, Turing Awards went to pioneers of AI, like the titans of the field, if you want, right? Like Herbert Simon, Alan Newell, Marvin Minsky, John McCarthy, people like that, right? And so, which was a completely different branch of AI, by the way, that was kind of the opposite a little bit, or the main competitor to the approach that is now dominant based on machine learning. Those were not based on machine learning. In fact, that's an interesting thing. Like Marvin Minsky had a big indirect influence on me. I only met him a couple of times, and he was kind of already retired more or less. But he was working on neural nets in the 50s. But then completely changed his mind in the 60s and decided that this was not the right approach, and that a different approach should be taken. And wrote a book with Seymour Papert in 1968 or 69 that basically killed the entire field of neural nets. The early attempts at neural nets, essentially. Writing all kinds of negative things about like how the limitations of those systems were, and that it really was not a path to AI, essentially. So it kind of killed the field, which is why when I started getting interested in this in 1980 or so, there was basically no one working on it. For the last 10 years, everybody had deserted the field because, it had been killed by Marvin Minsky. But here's the other indirect influence of Marvin Minsky. He was the technical advisor to Stanley Kubrick for 2001: A Space Odyssey. So the HAL computer was basically Marvin's idea of what an intelligent computer should be, which at the time was more like neural netty.
Right.
The movie script was written in the mid '60s, so I think he hadn't completely turned against the whole idea. But that's kind of he certainly had a big direct and indirect influence on me, both positive and negative, I should say. Seymour Papert, very positive, because I discovered the entire field because of an article that he wrote about language learning. So, yeah.
Yeah, it's a remarkable journey, and that's sometimes known as the AI winter, right? So, for some aspects, I guess not just neural nets, but just AI in general as well, right? Because it wasn't living to its promise. So you must be really excited by where it is now, and you're a big proponent of open source, open weight. So can you talk about that journey?
Sure. Yeah. So that's actually an interesting story in itself. So when I was at AT&T, we had developed a kind of a piece of software with my friend Léon Bottou on which we called Lush. At the time, it was called SN, but eventually it was renamed Lush. And that system is the ancestor of all the deep learning frameworks that we use today. So things like PyTorch. PyTorch is a direct descendant of Lush through another system called Torch, which was basically like PyTorch, but not based on Python, using Lua as a front-end language. And Léon and I developed this system, SN, which was basically a Lisp interpreter, which was used as a front-end language to kind of a back-end that was basically a matrix engine, right? Very similar to what we use now in PyTorch. And so we developed that system, and we wanted to open source it. And it was basically impossible to do in the 1990s because it wasn't really common for companies to open source software. There was a lot of open source software coming from universities, right? But not from companies. It really was not common. In fact, some companies were dead set against it, and even AT&T had some trouble. They had to sue Berkeley for Unix and things like that. It was like a complicated story. So we couldn't really open source it. We could only convince them to open source it when we left in 2002. So that tool, basically, we could not, kind of distribute. I mean, one big reason why neural nets were not that successful in the 90s is because we could not distribute software that could run it easily. And it's very difficult to re-implement it yourself because there's a lot of tricks, to kind of make those things work. And you don't really kind of write all those tricks in technical papers. So the only way to really communicate all that stuff is through a piece of software. We could not distribute it. So I suffered from the fact that, intellectually my impact was limited because I could not distribute the software that kind of run it. So I became kind of a big open source fan. Also, Linux was happening at the same time and things like this. Also in the late 90s, early 2000, Léon Bottou and I and Joshua and Patrick Hafner and a couple other people were working on a different project. I kind of stopped working on that because there was no interest from the community for it. So we worked on a project called DJVU. It was basically image compression technology to distribute scanned documents over the web. It would have been a good replacement for PDF if you want, except it worked for scanned documents, which PDF is not so good for. And at the time, it was, much, much better. So again, we battled with the lawyers at AT&T to open source the code, and they, didn't understand the point. And as a consequence, DjVu didn't have the success it should have had, which it would have if it had been open source. But because, we could not really kind of distribute the technology the way we wanted. So then I told myself, and then there was the story of, the convolutional net patents were basically stopping us from working on our own inventions because it was owned by some other company, right? So basically, I told myself at this point, I'm never going again to work for a company that stops open source, stops scientific communication, and then systematically patents everything, even if it doesn't have like a direct commercial interest. And so when in 2013, so that's one reason I went to academia. But then when in 2013 I was approached by Facebook, by Mark Zuckerberg and Mark Schiffer, who was CTO, when they asked me, like, can you join us and help us, like, start a research activity in AI? I told them, well, I have three conditions. The first one is I don't quit my job at NYU. Second one is I don't move from New York. And the third one is we have to practice open research, open source our code, and publish everything we do. And I explained why we had to do this, because that was the best way to make progress faster and also attract the best scientists. And their answer was wonderful. They said, oh, you don't have to worry about this. It's already in the DNA of the company. We already open source all of our platform software. Mike Schaffer, the CTO, who was going to become my boss, was his previous gig was basically head of engineering at Mozilla. So he knew the open source world inside and out. So basically, my response was, okay, where do I sign? That was a no-brainer, and really that philosophy has continued to this day, and now we see a lot of companies going from open to completely closed, like OpenAI, company like Anthropic being completely closed from beginning to end, and companies like Google basically climbing up. Right, there's fewer and fewer things that they're publishing, and as soon as it becomes there's a hint that it might be useful, they don't publish. And so I find that sad, because I think as we've seen with DeepSeek and Mistral and others, good ideas can pop up from anywhere. Yeah. And so if you are on an open source, open research community, it's going to progress faster. It's inevitable. That's what happened with Linux, and that's what's going to happen with foundation AI models today.
It's interesting. I was moderating a panel at AA Everything Global in Abu Dhabi in Dubai, and on my panel was one of the top startup founders out of Africa, and she was so excited about what DeepSeek did, because she says there's hope for smaller teams. Right. And it doesn't have to be a big corporation, a hyperscaler or something, right?
Well, that's a very important point to make. So people may not realize that, the first version of Llama 1, which was not actually technically open source, but it was kind of distributed researchers, it was developed in Paris by a small team of about a dozen people. Right. You look at the paper corresponding to Llama, it's 13 authors, almost all of them in Paris. And internally, what you have to realize is that there had been a number of, LLM projects at Meta going back 3 or 4 years before that, right? OPT-175B, which was basically kind of similar to GPT-3. But then before that, there was like a series of models by Jason Weston's group called Parlay. And so there'd been a bunch of LLMs of this type. In fact, in October 2022, my colleagues produced a chatbot LLM called Galactica, which was trained on the entire scientific literature. And it was designed to help scientists write technical papers. And it was really good at this. So they wrote a paper, put the paper on archive, put the code in open source on Hugging Face, and then also had a demo website where people could just, play with it. And it was doused with vitriol from the Twitter sphere. People on Twitter said, oh, this is horribly dangerous. It's going to destroy the scientific publication system. Now any idiot can, write a paper that sounds authoritative, and I can, have your system write a paper on the benefits of eating crushed glass, so people are going to get killed. I mean, people are saying like ridiculous things, right? And including some of those people were reputable scientists. And so the team that was working on this was a very small team of, 6 people or so. Couldn't sleep at night. And so they took down the demo. They kept the open source code and the paper, but they took down the demo. And then 3 weeks later, ChatGPT came out, and it was, like the second coming of the Messiah. So, and nobody understood, like, what's the difference? Like, why? And everybody was surprised by the enthusiasm of the public for this, including OpenAI. They were not prepared for, the kind of success that it met with. So there was a bunch of projects like this, and in 2022, maybe mid 2022, early 2022, FAIR had started a big project called Zeta for large-scale LLM, basically. And that project was doing okay, but not great. And then a small group in Paris kind of started implementing their own LLM using kind of completely different code base, and one group in Paris that was working on theorem proving picked up that platform and basically turned it into what became Llama. And it was a small team, right? A dozen people, as I said. And because it was not like an official top-down organized team, they turned out to be more agile and have more freedom to come up with interesting ideas because they could take more risks, right? And it's exactly the same thing that you see happening with DeepSeek, right? So you have big groups at Google, at OpenAI, at Meta, being under a huge amount of pressure from the market to produce, a new model every 3 months. And basically they are down in the trenches and they don't have the, kind of the leisure, if you want, to take risks and implement things that are not, you don't know are going to work, right? So next to that, you put a small team that has a longer leash, and they're going to come up with new ideas, and those ideas may completely change. So one story that's very important, I think, for people to learn about is the story of ResNet. So I don't know if you know what ResNet is. So ResNet is a particular way of building architectures of neural nets where basically by default, every layer in a deep learning system computes the identity function, okay? So you have basically connections going from input to output directly. You just copy the input on the output. And what the neural net is doing in between is basically computing a residual, a difference between the identity function and whatever it needs to compute. And the effect of this is that you can now stack hundreds of layers, and whatever a layer doesn't work or doesn't learn what it needs to, it becomes transparent. It becomes the identity function, okay? So the basic idea for this is a very simple idea conceptually. It's completely trivial in a way. But that paper appeared in 2015. And since then, everybody has been using this kind of architecture for any deep learning system. That paper came out of China.
Yeah.
It was, the first author is Kaiming He, who at the time was working at Microsoft Research Beijing. And, showed this, the results, coming from this architecture at ICCV in Chile. And everybody was stunned, like how well this thing was working. It's such a simple idea, like, makes a big difference. Now, that paper is the most cited paper in all of science in the last 10 years. All of science, okay? 250,000 citations in 10 years. It's been about 10 years. It came out of China.
Right.
Now, of course, a year later, I hired Kaiming at FAIR. He moved to California, and then he worked there, contributed to a lot of advances in computer vision at FAIR that were really incredibly impactful, used everywhere. And then less than 2 years ago, moved to MIT, so he's now a professor at MIT.
Yeah, that's a great story too, and it's about open science, right? And cross-pollination. I'm just going to do a time check. I think you have a hard stop at the top of the hour, or can you go a little bit beyond?
Yeah. I don't know if it's hard, but no, I have a bit of time, a bit extra time. We can take another 15, 20 minutes if you want.
Okay, that's great, because we haven't even started about where you think this thing is going, and there's so much excitement on kind of the neural net, the deep learning side, but you don't believe it's got to be something else. Can you talk about why you believe it's got to be something more than?
Okay, so yeah, I've been critical of LLMs. So first of all, I should say LLMs are great. They're useful. You know, we should work on them. We should have like big organization trying to push them as far as we can. Okay, that's the first thing. Second thing is they are not a solution to human level AI. We're not going to get to human level AI by just scaling up LLMs. This is just not happening. Okay. And there's several reasons for this. And I made this point before LLMs became, that successful. I published a long paper in 2022, before the ChatGPTs, etc. Basically explaining where I think AI should go. What are the essential characteristics of a truly intelligent system? And LLMs of the type that we have today, autoregressive LLMs, just do not have the right characteristics for it. They just don't. Okay. Here, there's two problems with LLMs. The first one is they cannot really reason, okay? We can coerce them into doing something a bit like reasoning by basically doing chain of thought. So essentially having them produce more tokens than they need to, essentially. So devoting more computation to complex questions than simple ones. And then the second trick is by having them generate like multiple sequences of tokens and then having a way of selecting which of those sequences is the best, right? And, DeepSeek R1 and things like this are based on this to some extent, and all the reasoning system that OpenAI has, do kind of things of that type. Now, this is not a good way to get an AI system to reason. It's been known for a very long time that the reasoning, in AI is a process by which you search for an answer. You don't just produce an answer by running through a fixed number of layers of a neural net. You search for the answer. Within a space of possible answers, you have some process, some algorithm, some procedure that searches for an answer that satisfies a number of criteria that accomplishes the task that you want to accomplish, for example. So in the context of robotics, a good example is motion planning. You want to get a robot arm to reach an object, for example, avoiding obstacles. So you have a cost function, which is, am I close to the object? Am I sufficiently far away from all the obstacles? Okay. And then you have a model of the robot dynamics that says, if the robot is in that position at that velocity at time t, and I apply this torque to all the joints, it's going to be at that position at that velocity at time t plus 1. And if you have such a model, then you can plan a sequence of torques that will get the arm to reach the goal while satisfying the constraints on the trajectory. That's motion planning. It's called MPC in optimal control, model predictive control. Similarly, in classical AI, the way you solve new problems is that there is a space of solution and you search through the space of solution which one actually satisfies the criterion. So it's basically an optimization process, right? And then, in older kind of AI approaches like Bayesian nets or graphical model, probabilistic graphical models and things like that, it's the same way. The way you infer the value of unknown variables is that you search for values of those variables that minimize some cost function, a negative log likelihood or something like that. At inference time, right? I'm not talking about learning, right? I'm just talking about inference. So this process of inference by optimization as opposed to by forward propagation to a neural net is intrinsically more powerful than just forward propagation to a neural net. And so we need to have systems that compute their outputs by optimization, not by autoregressive prediction. Okay, that's the first thing. So the first thing that tells you LLMs are not going to get us there. The second thing is we need systems that can learn from the real world, because there is way more data in the real world than there is in text. Okay, so you take the totality of all the text publicly available on the internet, and that's roughly 20 or 30 trillion tokens if you tokenize the words, right? Token is typically 3 bytes, so that's 10 to the 14 bytes. Okay, it would take you or me maybe 400,000 years to read through it, maybe 500,000 years. Okay, it's enormous, right? It's all the text available on the internet. But that's produced by humans. And in fact, not all of human knowledge can be represented in text. In fact, most human knowledge is not representable in text. It's our experience of the world, of the physical world. Okay, now compare this with what a 4-year-old child has seen during his or her life. A 4-year-old has been awake a total of 16,000 hours. Each optical nerve carries about 1 megabyte per second or so, and we have 2 of them, so it's 2 megabytes per second. It's 1 byte per second per optical nerve fiber, and we have 2 million of them. So do the arithmetics, and in 4 years, a child has seen about 10 to the 14 bytes through vision, similarly through touch. And so that tells you that, it's 100,000 times less time than text. If you were to get the same amount of bytes through text, it would take, it would take you 400,000 years. And so what it tells you is that we're never going to get to human level AI systems by just training it on text. It's just not happening. And there is much to learn by basically experiencing the physical world, learning from video. I mean, babies learn by just observing the world. In the first few months, they don't even interact with it. They just observe. And they accumulate an enormous amount of background knowledge about the world. Now, here's the bad news. You can't use generative architectures to learn from video. It doesn't work. We've tried. I've worked on this for 20 years, right? So, I mean, the idea that, you take a piece of text and you train a system to predict the next words in the text, it works amazingly well. And it works amazingly well because text is discrete. You only have a finite number of possible words or tokens, right? So you cannot predict exactly which word comes after the sequence, but you can predict the distribution over words, right? But if you try to do this with video, try to predict what's going to happen in the video, you basically can't do it. You're facing, intractable mathematical problems, basically, of representing distributions over high-dimensional continuous spaces. And we just don't know how to do it. And so I've been struggling with that problem for a long time. And then a few years back, realized that the architectures that actually work to learn representations of images are not generative. They are architectures that do not work by reconstruction. They work by what's called joint embedding. So instead of training a system to predict what's going to happen in the video at the pixel level, you train the system to learn an abstract representation of the content of the video, and you make prediction in that abstract representation space. The hope is that in that representation space, much of the complicated stuff that you can't predict that occurs in the real world will be eliminated, so that the stuff you preserve is the stuff you can actually predict. So that type of architecture is called Joint Embedding Predictive Architecture, JEPA. And my collaborators and I have been working on this for the last 4 years, roughly 5 years, and are starting to get some really good success with this, of systems that really understand what goes on in the video, systems that have acquired some level of common sense and intuitive physics, and they can detect when something impossible occurs in the video, like an object changes shape or disappears or, behave strangely. We just had a paper actually posted on arXiv about this topic. So we're really, really hopeful that this will lead us to, systems that can learn from video. And then the next step, which we're also working on, is world model. So what is a world model? It's a system that, learn an abstract representation, maybe a video or the real world, but then has a predictor that, given the state of the world at time t and an action that you imagine taking, predicts the state of the world at time t+1. If you have such a model, then you can do planning, you can do reasoning. All of our reasoning is done with mental models of the world. And that's what we're trying to reproduce with machines. So there, once we make significant advance in that direction, I think we have a good chance of knowing whether we can reach, maybe cat level AI, maybe dog level AI, maybe human level AI sometimes in the future. But it's not going to happen next year. The declaration that you hear from, Dario Amodei or others, we're going to have PhD level intelligence next year or the year after next. That's just completely stupid. That's completely ignoring the mass of enormous amount of knowledge that comes from the physical world that gives us common sense. So yeah, we're going to have systems that can solve math problems, perhaps at the level of, a PhD student or something. But that's a very narrow field. Where is my domestic robot? right? Where is my self-driving car? Like if we really had human-level AI, we would have a system that can learn to drive a car in 20 hours of practice, which is what most 17-year-olds can do. And we don't. So that means we're missing something really big.
So, Jensen last month announced the Cosmos open source world foundation model. Is he looking at your JEPA architecture at all?
No, it's, yes and no. So there's various approaches to building world models, and a lot of people are getting interested in this. I've become interested in this in the last year or so. So there are models that, where you learn a representation of frames or videos in a self-supervised manner, but like in a kind of separate step, if you want. And now you have a feature extractor, and you can use that representation and train a predictor for particular environments. Okay. And we've worked on this. We have a recent paper, Dino World Model, which uses pre-trained, self-supervised pre-trained representations called Dino. This is also done by colleagues at FAIR Paris. And then on top of this, we train a predictive model for planning. This works. It seems to work pretty well. So there's one idea, which is you pre-train a representation and then you train a predictor in it. The idea that I think is the most interesting long term is you train the encoder and the predictor simultaneously. So that's this JEPA architecture. So we have this technique called VJEPA, which can train this kind of architecture altogether. But there is a number of approaches where people are insisting that the proper way to do this is to get the system to predict at the pixel level. Okay, so basically they're saying the best way to train a world model is to predict what's going to happen in the video at the pixel level. Maybe you're going to tokenize a video the same way you tokenize text. Okay, and then train a LLM-like thing to kind of predict what happens in the video. And then you have systems like Sora that use, diffusion models and things like this, because, you have to use diffusion models if you want like good looking video. But ultimately, my argument is you should not attempt to predict everything that happens in the video, because most of what happens in the video is not predictable. And so those models, there's also a model from Google, which works well because they trained it on video games. So video games are, there's not a huge amount of like unpredictable things that happen at the pixel level in video games. So there it works okay. And we've had models like this, some of my work at NYU with my students, we had video prediction systems that worked okay for like, stylized video, if you want, where like semantic video, if you want. They're not like completely natural videos, but it's very limited. So if you want, a completely general method, I think you should not attempt to do prediction at pixel level. We actually had a big project at Meta at FAIR called Video MAE. So this was based on the idea that you would take a partially masked video and then train a gigantic neural net to predict, the missing tokens basically in that video. We canceled it. It just wasn't going anywhere. So it was burning a lot of GPU cycles, but not really working very well.
I mean, you'd think that Jensen's group, though, would start looking at what you're doing, and they must be some other researchers looking at your work. Or didn't you do something called the large context model, which must have some elements of this in it? There's Agribot World, they launched an open source platform. You think that some people within the community would look at what you're doing? You have the Helix model, which is it's an a visual action model in their theater. They just released it. You'd think they'd be starting to look at some of your work. There's got to be teams looking at your work, right?
There's quite a few people working on JEPA-like systems, right? There's certainly some people at DeepMind. Daniel Hafner has a system he called Dreamer V3, etc. And it has this idea that you train a representation system, and then you use prediction in representation space to do planning or learning a policy or something. So it has a bit of that flavor. It's not as extreme as the kind of stuff I'm proposing. There is a model from Wave. So Wave is a company spin-off of Oxford that works on autonomous driving, and they have a model called Gaia, which kind of is similar. You also kind of pre-train a representation using VQAE, and then you train a predictor in that space. I think it's a little inspired by some of my proposals. Although they train this representation using a autoencoder, which I think ultimately is not the thing you want to do, but okay, you have to start somewhere. Within FAIR, there is other projects. There is the LCM, which means latent concept model, which basically is a JEPA-like architecture for text, but it's also trained by reconstruction, which you can do for text because text is easy to predict. And various other groups have been sort of playing with those ideas, but there is this sort of mental block. Maybe it's a herd effect. Maybe that everybody's talking about generative models, so everybody is using generative models as a tool, and everything looks like a hammer, and you have to use that. And so a lot of people are not willing to put in question the whole idea of generative prediction.
Yeah, it's like Minsky kind of ruled the space, right? So you're trying to break through this deep learning kind of mindset and saying, hey, you got to look a little bit broader, right?
Yeah. That's a bit of the story of my career. It's to be a little bit outside of the mainstream. So, I've become the mainstream, but then it's boring. So you have to kind of come up with some other new idea, like, go to the next step. And so this idea of, inference by optimization, which is nothing new, absolutely. And the idea of world model, nothing new either, it's a very old idea in the concept of optimal control and motion planning. And this idea of kind of learning this whole thing end to end, that's relatively new. The idea of joint embedding architecture is not new. I had a paper on this in 1993 for what was called at the time Siamese networks. And you can think of those JEPA architecture as kind of the descendant of this, but there are architectures where you don't train them supervised. You don't train them. You train them basically by, you have two observations, X and Y, and you want to somehow predict Y from X. But there might be multiple Ys that are compatible with an X. So you run both X and Y through encoders, and then you do that prediction in that space. That's the idea of JEPA. That's the idea of joint embedding. And what convinced me this was the right approach over the last 5 years or so is that all the empirical results that we've obtained to use self-supervised learning to train an image representation or video representation systems, all the ones that work well are all joint embedding architectures. None of the ones that work by reconstructions actually work. So autoencoders don't work very well. Mass autoencoders don't work very well. The ones that work well are all joint embedding, and they don't actually attempt to reconstruct.
So when is going to be your ImageNet, AlexNet moment where the world recognizes? Right.
I don't know if it's going to be like
this is the way to go.
Yeah, I don't know if it's going to be a single moment. I think it's going to be like more and more evidence that those things work. And truthfully, it was the same for image recognition back in the early 2010s. We had a lot of applications of convolutional net that were starting to work really well, and people were just dismissing those results, right? So like an interesting story in I think it was 2010, it was 2011. We submitted a paper to CVPR, and
which is the number one image kind of vision conference, right? So
computer vision pattern recognition conference, the premier international conference on computer vision, right? And that paper was using convolutional net to do what's called semantic segmentation, right? So you show an image, and then the system labels every pixel with the category of the object that the pixel belongs to, right? So if you have a scene from a street scene, for example, it would label the street, the sidewalk, the walls of the building, the trees, the pedestrians, the bikes, the cars, the trucks, everything, right? And And there was a relatively small data set that we could use to train our convolutional net on, which had something like 2,000 or 3,000 images that were like carefully labeled, by region, by Antonio Torralba and his collaborators. And so we used that data set and got really good results on this, a bit better than what people were doing at the time, and with a system that was running 50 times faster than the best runner-up. It was running it basically in real time on a laptop. And the person in my lab who was working on this was Clément Farabet. He's now a VP at DeepMind, Gemini. He was at NVIDIA for a long time as well. And he actually developed an FPGA board to run this like super fast in real time. That was pretty amazing stuff. And so we write a paper, submitted to CVPR, and this was the first time I was certain like the paper was going to be accepted as an oral.
It gets rejected, right?
It was soundly rejected by all 3 reviewers who said, like, this is ridiculous. How come this method we never heard of? Can work so well. There must be a mistake somewhere. And why would you learn features when you can hardwire them? I mean, it was like, this was before the deep learning revolution. So people hadn't kind of changed their mind yet about this. And so we did not even respond to the reviewers. I wrote a letter to the program chair and said, like, there's no point, like, it's completely hopeless. And I'm going to tell my student, don't even think about submitting to computer vision conferences anymore because they're just not ready. Like, they don't know enough about neural nets to really be able to have an informed opinion. So we submitted it to ICML, and it got accepted to ICML in 2012. And then at the end of 2012 was the ImageNet revolution. And in 2013, everybody in computer vision stopped whatever it is that they were doing and started to use convolutional net. And in 2014, you could not get a paper accepted at CVPR unless you were using convolutional nets, right? So, so it's kind of an interesting, funny story. But that's the way science and technology progresses. But you're going to be careful not to be too prisoner of the current fashion.
Yeah, and then you've gone through a lot of hardships, sort of bucking the trends, and you got to make sure that you're encouraging your fellow colleagues to have an open mind. Right? So,
yeah,
open science, open mind, right? So I know we're at the borderline. You kindly extended. We're 13 minutes past the hour, and I know you have to go to a really important other meeting. So, is there any area that you want to bring up, just in a kind of a free space for a few minutes, and then? The last question would be, what's your recommendation? So the 2 final questions.
I'm not sure I have a bunch of recommendations, but I'll start with the importance of open source. So, a lot of countries around the world want to use AI for various things. And the only way for them to be able to do this at the moment is to basically fine-tune an open source foundation model. Llama, Mistral, DeepSeek, whatever. What I see eventually is that the open source world is going to coalesce into essentially 1 or 2 or maybe 3 basic foundation models, and that the training of this foundation model will be collaborative and distributed. Because, we need those systems to basically speak all the languages in the world, understand all the world's value systems, and centers of interest and cultures, and no single entity, as big as it is, can have access to all the data that is necessary for this. So the best way to do this is to partner with people in Africa, India, Middle East, Europe, various parts of Asia, and they would be contributing to training this global system, okay, in a distributed fashion. So basically, they would retain control over their data. They will have a local data center, which they could use to train a global foundation model on their data. And what they would communicate is not data, but it's parameter vectors. Okay, so in the end, you would have a global foundation model that is a consensus between all of those local models that would be usable open source for everyone and would understand all the world's languages and cultures and value systems. Okay, that's the future I want to see. I don't know what the best way to do this is, but the first step is certainly to not just enable open source, but favor it because it's necessary for this to occur. Certainly, you want to tell governments around the world that they should have a deliberate policy to favor open source, and they should certainly not have regulations that will make it illegal. I mean, some people like Dario Amodei are basically scaring governments around the world of saying, AI is super dangerous, and so you should keep it under control. So open source, should be banned, essentially. And I think that's incredibly destructive, and in fact, extremely dangerous, because in the end, we would get just a handful of AI assistants that everybody will get their entire digital diet through. And if they come from a handful of companies on the West Coast of the US or China, I mean, we're done with, cultural diversity and democracy and everything like that, right? So this is not a future I want to see. So open source is really important for that reason. I think people in academia and various research organizations should not be working on LLM. LLMs are now in the hands of industry. There's enormous teams with gigantic computing resources working on it. Academia should work on the next step, the next thing beyond LLM, not LLM themselves. That's in the hands of industry now. It's not fun anymore as an academic to work on this, unless you want to just do analysis and stuff like that. But what's the fun in that? So that's my second recommendation. And the third one is, if you really want to innovate, have breakthroughs, you cannot have breakthroughs that are pre-programmed, right? You can't just, build a team of 20 people and tell them, okay, I want the next innovation in 3 months. Because you can't, take any risk if you have to guarantee having some result in 3 months. So there is a mode, which is a product mode, where that kind of top-down specification works. But if you really want innovation, you need a longer leash. You need to let people take risks and innovate. And then if you really want breakthroughs, you basically need a research lab where, with a very long leash, very little pressure from above, a clear long-term goal, okay? And that's what I've been trying to basically reproduce at FAIR. I say reproduce because I experienced this at Bell Labs. This is the way Bell Labs operated to a large extent. And, the result of all the big technological innovations of the modern world, came out of Bell Labs, like many of them. So there's certainly a big record of success. So that's an important thing. And we see, an example of this with DeepSeek. A small team, a lot of freedom, they come up with new ideas.
Those are really great recommendations from open source. They're having this freedom to innovate and not be so top down and very distributed and kind of thinking. And what DeepSeek did is they actually hired really young researchers who had no resume.
Yeah.
But were really good at, just thinking outside the box. So, Jan, I really enjoyed this interview. I mean, I've done these things for 50 years, and it's probably the one that stands out the most. Incredible work you're doing, and I'm going to definitely proliferate this through all the CEO and all these other conferences I do. Just thank you for coming in and going beyond our time limit as well. So I appreciate it. Thank you again.
Well, thanks to you. Thank you for having me on. That was fun.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for The Brand Called You.